Hello and welcome to Honors Function. This is the first video of a series of lecture where we're going to be looking at the behavior of polynomial function. In this video, we're going to be looking at a global behavior of a function. Global is opposed to local. Global means it's not going to be for a very specific value of the input, but for a subset of the real number. In this case, we're going to be looking at the end behavior. So let's start. So what does it mean to look at the end behavior of a polynomial function? So we're going to be given a polynomial function. So the generic notation would be an xn plus a1x plus a naught, right? This is a standard form. Looking at the end behavior means we're going to be looking at where f of x goes as, so the end behavior means x approaches plus infinity, or x approaches negative infinity. Okay, x approaches plus infinity, we write it as x tends towards or approaches plus infinity, like that. And x approaches negative infinity, of course, we write it as x approaches or tends towards negative infinity. Now if it's plus infinity, we often don't write the plus, okay? It's just infinity. Okay, and we have a very specific notation for that to indicate, actually I guess I should have a question mark here, where, and the notation for that is the limit notation. So this is a very important notation that's not going away, especially important in calculus. It's the first time you're looking at it. So this question right here, we write it like that. Where are the f of x? So we write the limit of the output f of x as x approaches, so here it's going to be plus infinity, and here we're going to have to describe where is this limit, what are the outputs, okay? And or limit of f of x as x approaches negative infinity, okay? And here we will write the results of our investigation. Okay, you're going to have to find out if there is a limit, and if there is a limit, what it is, okay? So this is a very, very important notation. It's not going away. So please make sure, here's a line, if you have a line on your paper, limit goes right here, okay? F of x is right next to limit, like this, and x approaches plus infinity ought to be written under limit, okay? X approaches, and here I write plus or minus infinity, like this, all right? Don't write something that is not resembling to that. You got to make sure you're using the right notation. Okay, so this is what we're going to be doing in this lecture. This is called the end behavior. Okay, we're going towards plus infinity or negative infinity. It's the end behavior, and it's a type of global behavior. It's a type of global behavior, again, as opposed to local behavior. Okay, here we go. First point. Second point, before I do this, I need to describe two very important properties of polynomial function. Any polynomial graph is continuous, and smooth. These are very technical words. They have an analytical way to measure continuity and smoothness. We do not have the tools to measure continuity. Actually, continuity is about some limit notation, okay? But we just introduced the notation of limit, and we don't have the tools in this course to really delve into the technicality of continuity, nor do we have the tools to delve into the technicality of smoothness. Here you would need some limit, but you would also need some derivative, okay? Derivative. So we don't have the tools to do that. So I just want you to have an idea of what continuous means, okay? And what it doesn't. If you encounter a function that is not continuous, I want you to be able to recognize it. Continuity means you can draw the graph of the function without lifting your pencil. Here we go. I just drew the graph without lifting my pencil. So an example of a function that is not continuous, well, you would have to lift your pencil, right? So you may have, for example, you may have a vertical asymptote, right here, and then the asymptote would be there, and then you pick up either here or at the top, like for example this right here. See, you had to lift up your pencil. Another example of a function that is not continuous, we've seen it before, would be either a piecewise function, right, that is not continuous. It could be continuous too, but a piecewise function that is discontinuous, for example, part of a parabola here, and then here you would have like a linear function. You have to lift up your pencil right here, right? Or finally, you could also have a step function, right? You remember these ones? The greater integer function, the floor function, This is not continuous, all right? What does smoothness mean? Smoothness means there is no sharp turn. So of course, this is a parabola. It doesn't have any sharp turn. Or this right here doesn't have any sharp turn. So what kind of graph has a sharp turn? Well, you know one, okay? You know one very well. For example, an absolute value graph. Now this is a sharp turn. This is not smooth. Another type of graph with a sharp turn would be something we call a cusp point. So for example, something like this right here, okay? This is another sharp turn, all right? Again, we do not have any tools to measure it, so I just rely on your conceptual understanding, intuitive understanding of continuity and smoothness. Two very important concepts. Please now go over example 1 through 4. Here are example 1 through 4. I'm going to let you do them all on your own. You have to decide which graph is continuous or not continuous and smooth or not smooth. And you also have to decide which could be the graph of a polynomial function. Remember, a polynomial function is smooth and continuous. Okay? Now let's take a look at the end behavior of a polynomial function. All right. Here is the generic form of a polynomial function. The degree of this polynomial is n. We're going to assume that an is not 0. Okay, so the degree is n right here. The next term, if an minus 1 is not 0, the next term is the monomial of degree n minus 1. What I'm asserting here is that as x gets very, very large, this is going to carry most of the weight for the output of the function. Why? Because it has a degree of n, while the next one has a degree of n minus 1. And that's going to be much smaller if n is very large. Let's take an example. All right, let's look at this cubic function. I want to show you why this monomial, we call that the leading term, carries most of the weight for the output, okay? So let's take the function g of x equals negative 3x cubed, and we're going to try to understand why these two functions are very similar when x is very, very large. Let's take, for example, x equals 100, okay? What is 100 cubed? What is 100 cubed? Well, it is, you take 100 and you add two series of zeros like that, so it is 1 million. What's the next term? And then you multiply by 3. That doesn't matter, right? What's the next term? The next term is a square, right? What is 100 square? Well, 100 square is just 10,000, right? So what's the ratio of this term to this one right here? What's the ratio of 10,000 to a million? Well, the ratio is very simple. Take away 4 zeros and you have 1 to 100. It's 1%. It's 1%. So the next term, if x is 100, the next term is just 1% of the leading term. It's pretty small, and 100 is not a very, very large value, right? You can imagine if x is 1,000 or 10,000, that's going to be even bigger. Let's try to see graphically what that looks like. So I have, in my calculator, I have plugged in these two functions, f of x and g of x, and let me look at the graph in a standard window, okay? So in a standard window, the graphs look like this. In blue, you have f of x, and in red, g of x. So it is not very good. Let me increase my y min, y max. Let me not change my x min, x max, but y min, y max, I would like negative 50 and 50 right here. Let me also change my y scale to maybe 10. I don't want too many tick marks. on the y-axis. So let's look at the graphs now. Here's f. All right, and here is, well, okay, here we go. And here's g. Now these two graphs do not look alike, right? They're very different. Okay, now let's look at these two graphs from another point of view. Now you're gonna see this is not infinity, because I'm just going to negative 40 on the x mean, and x max I'm gonna take plus 40. So it's far from being infinity, right? Let me take a 10 for the x scales. And for my y mean, y max, I'm gonna go 1,000 times bigger than that, so negative 50,000. And I'm gonna take 50,000 for the, where am I? Right here. 50,000 for the x max. And on my y scale, I'm gonna take, I guess, 10,000. Here we go. Oops, another one. All right, another one. Here we go. Let's look at the graph. That's f, and that's g. Now, of course, we lost information right here in the middle, right? We lost information for smaller value of x's, but look, these two graphs really look very, very, very similar. And again, I am not very far. The x mean is just negative 40 and the x max is 40. So it's almost the same thing. And we're not at negative infinity or plus infinity, okay? All right, so let's describe this with a statement that I will not prove. Here is an important statement in this lesson of this lecture, is that the behavior of a polynomial function as x approaches plus or minus infinity is the same as the behavior of its leading term, okay? One way to write this, and I guess I should have written it here, I didn't write it, we would say that the polynomial anxn plus a1x plus a0, and here's a notation we use in math, we say it is equivalent to, that means equivalent, at, you have to say where, at plus or minus infinity, it is equivalent to its leading term, its monomial of highest degree. Okay, so if you want to study the end behavior of a polynomial function, you just need to study its leading term. Let's do that. Let's study what happens to the graph of a function as x approaches plus or minus infinity. So we need to be looking at 4 different cases, okay, depending if n is odd or even. That's going to be one type of behavior, and then the second case depending if an is positive or negative, right? So there are 4 cases. Let's try to look at these 4 cases individually. Okay, let's start with n odd. First case, an positive. So if x approaches plus infinity, if you raise x to the power of n and n is odd, you're still going to approach plus infinity. And if now you're multiplying this very large positive number by a number that is positive, you're still going to approach plus infinity. So this is the first type of n behavior. Let's look at the second one now. If x approaches negative infinity, what happens if you raise a very large negative number to an odd power, cube, power 5, power 7? Well, it's still going to be negative infinity, right? And then, if you multiply this negative, very large negative number by a positive number, you're still gonna go to negative infinity. So, the type of n behavior that we have here is this one. It's going down as x approaches negative infinity, y goes down. And as x approaches positive infinity, y goes up. I don't know what happens in the middle. It doesn't matter. But this is a type of behavior, okay? So basically, we have a graph from the bottom left to the top right, okay? Let's look at the second one now. If an is negative, so as x approaches infinity, if you raise x to the power of n, you're still going to approach infinity. And now if you multiply this very large positive number by a negative number, now you're going to approach negative infinity, right? All right. And if x approaches negative infinity, what happens if you raise this negative infinity to an odd power? It's still going to be negative infinity, but now you're multiplying this very large negative number by another negative number. Two negatives makes a positive. You're going to be approaching plus infinity. So what does the end behavior of the graph look like? It looks like this. As x approaches negative infinity, y at negative infinity, y is positive infinity. It goes up like here. And as x approaches positive infinity, y goes down like that. Now again, I don't know what happened in the middle, okay? But I know in this case, my graph would go from the left top corner to the bottom right corner, okay? So we are in the case of n odd. What is the easiest odd function? Polynomial. The smallest, it's a line, ax plus b, right? This is odd. And we call that the slope of the line. This is a very good mnemonic way to remember it, okay? Basically, if you are dealing with an odd graph, an odd polynomial, it acts just like a line. If the slope is positive, it's like this. If the slope is negative, it's like this. I'll show you how to think about it with some examples later. Let's go over the last two cases. So, if n is even as x approaches plus infinity, if you raise a large positive value to an even power, it's still gonna be plus infinity. And now if you multiply this by a positive number, it's still gonna be plus infinity, okay? All right. Now, as x approaches negative infinity, if you raise a large negative number to an even power, it's gonna be a positive number, right? It's going to be a positive number. And you multiply this positive number by another positive number, it's going to be a positive number right here, very large positive number. What does this end behavior look like? Well, in both cases, you will be at plus infinity. I don't know what's going on in the middle, right? But I'm at plus infinity in both cases. And now for the last one, hey, I'm gonna let you work the detail here, but in the last case, you would be at negative infinity for both, like this, okay? And what is the smallest even degree, right? We're n even now. What's the smallest even degree? It's a parabola, right? Ax squared quadratic function plus bx plus c. And we know that a dictates the concavity of the parabola. So that's one way to remember it. Parabola concave up, parabola concave down. Now, of course, you know, if n is 4, it's not a parabola. It's just a mnemonic way. Okay, let's go over some examples and we'll be done. So in here, I have given you some solved example. So you can see right here, you're dealing with an odd function with a positive leading coefficient. Odd function, positive leading coefficient. I'm thinking of a line, right? I'm thinking of a line because it's odd. And I'm thinking of a positive slope. Check it out. It's a line going up. And here, another odd with a negative slope, line going down, right? And for these, it's an even function, so I'm thinking parabola, and I'm thinking concave up, like this, right? And here, even function, concave down, parabola, concave down, like this, okay? Again, actually, this function right here is not just concave down, okay? Sometimes concave down, sometimes concave up. This is just a mnemonic way, all right? Okay, let's now go over some examples where we use the limit notation. All right, I'm gonna do 2, and you're gonna do 2. Okay, what is the limit of f of x as x approaches negative infinity? And what is the limit of f of x as x approaches positive infinity? Well, let's see. This is an even polynomial, right, degree 4, with a positive leading coefficient. So what am I thinking about? I'm thinking like a parabola concave up, like this. Okay, I don't know what's in the middle right here. I'm thinking like a parabola concave up. Therefore, both limits will be positive infinity and positive infinity. That's the way you write it. Please do example number 6. Let me go over example number 7. Okay, example number 7. Again, I need the limit of h of x as x approaches negative infinity and the limit of h of x as x approaches positive infinity. What are these two limits? Again, we need the end behavior. So we need the leading term. What's the leading term? Oh, I need to do a little bit of work here. So let me see. For the leading term, I have a negative sign, right? Don't forget this negative sign here. Negative sign. Here I have a negative x cubed that I'm raising to the power of 5. And here I have a negative 2x4 that I'm raising to the second power, right here. So what is that? I have a negative sign. This negative power 5 will stay negative. And then I have x to the 15 right here. This negative sign raised to the square is going to be positive. And here I have x to the 8 right here. So 2 negative makes a positive. I have x to the 23 odd power of, I forgot my, it doesn't matter, right? It's a 4. It's positive, right? I'm not interested in the number. I'm interested in the sign, okay? So it's positive. So odd means it behaves like a line. And positive slope means it's a line going up. All right. So at negative infinity, as x approaches negative infinity, my y will be at negative infinity. And at positive infinity, my y will be at positive infinity. That's it. Thank you for watching.